Okay, so when we fit a line to our scatter plot of data, we made some assumptions on the errors. That is that they have a mean of 0 and that they vary the same no matter where you are on the line. Now we're going to add an additional assumption to this. We're going to add that those errors are also normally distributed. So we've got our same model for regression. We've got that conditional mean is the line that fits through the population scatter plot of the data. And there's going to be scatter around even that population line, and that's these errors. And so instead of only assuming that there are just as many above as there are below and they kind of cancel each other out and balance each other out, that is, they have mean 0, and that they vary the same no matter where they are on the line, we're going to say that they vary according to a normal distribution around that line. So here's a picture of what we're talking about with those three assumptions. If this was your regression line, right here, you're going to have some points above and below the line, right? So what we're saying now is that on average, they're right on the line. That's the errors have mean 0. And that they vary the same, that the variance of these normal distributions is the same no matter where you are on the line, and that they vary according to a normal distribution, meaning most of them, 68% of them, are clustered here within one standard error. 2 standard errors is about 95% of the observations, and within 3 is 99.7% of our errors. Okay, so the assumptions that you're going to check are the same as they were for ANOVA, as they are for ANOVA. The errors have to be independent, normally distributed, have an equal variance no matter where you are on the line, and have mean 0. So if these regression assumptions hold, then we can start making inference on, for instance, our slope. So we can make a test statistic by taking B1 minus the null hypothesized value of it, which is 0. We'll talk about that in a minute. And divided by the standard error of B1. And so it's done, computed just like our other test statistics, but of course we're going to let a computer do it. Remember that the t-distribution for regression is n minus 2 degrees of freedom instead of n minus 1, and that's because we're estimating two parameters. We're estimating beta naught and beta 1. The null hypothesis when you're testing for the slope is that the population slope equals 0. And what does that mean? That means that if your slope has 0, it looks like that. And that means that the mean of the y's does not change as the x increases. So y doesn't have anything to do with x. The alternative is that it's either greater than, less than, or not equal to 0. And then we can create a confidence interval in much the same way that we did before. Our sample estimate of our beta 1 is B1 plus or minus a margin of error comprised of a t-critical point times the standard error. So the typical same test and height and confidence interval that we learned before. All right, so we're going to work with the personal record data that we've brought up a couple times already. This is for 23 members of Body Shop Athletics X in Irmo, South Carolina. And a personal record is the highest amount ever lifted or pressed for these weightlifting maneuvers. The weightlifting maneuvers recorded here are the deadlift, where the weight is loaded onto a barbell, lifted to the hips, and lowered again, and the bench press, where the loaded barbell is pressed up from the chest as the athlete lays on a bench. So we've got some pictures of those weightlifting maneuvers in case you were not familiar. And there was a time that I didn't know what they were also. And then we've got our data over here. Of course, I have it in R format for you to download so you can pull it into R and follow along. So I made a scatter plot of the data. Bench press is my X, and my Y, my response variable here, is deadlift. And we can see that it looks reasonable, that it's linear, right? So I went ahead and fit a line to it. And it doesn't look bad. So then I went ahead and fit my regression line in R. So how I did this was I always call my fitted models fit, and I did LM instead of AOV because we're in linear regression, my Y variable, which is deadlift, tilde my X, which is bench press. And I have my output here. So notice, again, same output that we had before. You get your intercept, and then you get your slope multiplied on your X variable, bench press. And of course, you've got your residual standard error, multiple R squared, and all that other good stuff. All right, so let's check the assumptions. So The errors being independent are going to have to be checked by other plots that we're not going to go over right now. We'll talk a little bit more about that when we get to time series. But for now, we're just going to have to assume that the errors are independent. And the other three assumptions we can check with these two plots. The first one is called a residuals versus predicted plot. And so what I've done is I've taken the fitted values of the fitted model and plotted them against the residuals from the fitted model. So basically, this horizontal line that I've drawn at 0 is like your regression line. If a point has a positive residual, it means it was above the regression line. If it has a negative residual, it means it was below. So if we take a look at our scatter plot, we can see that this one's going to have a positive residual, this one's going to have a negative. So the residuals versus predicted plot is basically like pulling this regression line down flat, so we can really tease out what's going on in the variability of the points around the line. Okay, so that's what our residuals versus predicted plot is. And we're going to check two assumptions with that plot, that the errors have mean 0 and that they have constant variance. So what does it mean that they have mean 0? It means that any slice of x, if I average together those residuals, would they cancel each other out to be 0? On average, do they look balanced above and below the line? And I would say yes. Not too bad. At every slice of x, it looks like they're fairly balanced above and below the line. So I'd say little to no evidence against the errors having mean 0. Little to no evidence against the errors having mean 0. And I'm going to check that it looks like they're just as spread out no matter where you are on the line. Now, when we look at our scatter plot, you can kind of see the variability is roughly the same no matter where you are on the line. But we can also see that on the residuals versus predicted plot, right? Anywhere we are, it looks like they're just about as spread out as each other. Now, a rule of thumb that we're going to use is if you can move 1 or 2 points and make it look perfect, we're going to say it's probably okay. And if I could move this point here and this point here, I'd be a lot more happy. I'm going to say that this is little to no evidence against the errors having equal variance. So again, little to no evidence against errors having equal variance. And the normality assumption is going to be checked with a QQ plot. Now, a QQ plot is linear if the data come from a normal distribution. So if the data come from a normal distribution, this QQ plot is going to be linear. Anything that's really far from linear, like a U shape, or an upside down U shape, or an S shape, or an inverted S shape, is going to be evidence against normality. But here, it looks like we're okay. If I squint my eyes and make it kind of blurry, I don't see any glaring shape standing out to me. It's basically linear. So I'm going to say again, little to no evidence against errors having a normal distribution. Okay, so there's our assumption checks. Not bad. This one passes the test okay. So now we're going to carry out a hypothesis test at the 5% level for the slope equaling 0. So step 1 is stating your alpha level, so we're going to say it's 0.05. The null hypothesis in regression is that the population slope is flat at 0. And the alternative that's tested by default in R and many, many other software programs is that it's not equal to 0. It doesn't specify a direction, it just says it's either positive or negative, it's not 0. All right, so we can get our test statistic from up here in the output. And you'll notice that in the line that goes with my slope coefficient, I not only have the estimate of the slope, I've got the standard error, and I've got my t-test statistic for my test. So my test statistic is 10.925, and my p-value is 7 times 10 to the negative 10th power. It's very, very small. So that means it has 9 zeros and a 7. Really, 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 really tiny. So obviously, P is less than alpha. And if the P is low, the null must go. And so what are we going to conclude? There is evidence for the alternative hypothesis. Whoops, I somehow changed slides. So this is for the example of not equal to. All right. So obviously we have evidence for the alternative hypothesis. There is overwhelming evidence our P is really, really small. To conclude, we want to put this in the context of the setting. So what is beta 1? Well, that's how the average y changes with an increase in x. What's our y here? It's the deadlift. So to conclude, mean deadlift changes with an increase in bench press. Okay, so now we're going to do our hypothesis test for the alternative of greater than. I'm not going to write out all the steps because we just did that. The only thing that's changing here is our alternative hypothesis and therefore our p-value. So let's think about what R gave us. So R gave us the p-value from R gives us the p-value for the two-sided test. And that means that it looked at the area to the right of positive 10.925 and the area to the left of negative 10.925. And it added those two areas together and said that it equaled 7 times 10 to the negative 10th. Okay? But we want the p-value for the alternative that beta 1 is bigger than 0. So how do we get a p-value for the greater than alternative hypothesis? Well, we plunk down our test statistic and we go in the direction of the alternative, which here is greater than, to the right. So we just want that area. Now we know how we can find that number. It's 1/2 of the p-value that's given for the two-sided test. So the p-value here is 1/2 of that really small number. And that's how you find the p-value for the directional alternative hypothesis. And of course, we're going to come to the same conclusion. There's overwhelming evidence to conclude. And this time you would say, let's go ahead and write that down. There is overwhelming evidence to conclude, well, and I guess I could say my p is really, really small. I'm just going to say it's less than 0.001. To conclude, mean deadlift increases, because we were looking for a positive slope this time in our alternative, with an increase in bench press. All right. So I guess we had a couple things change. The alternative changed, so the p-value changed, and so did our conclusion. All right, so that's our example on a hypothesis test for the slope. And now we're going to talk about a confidence interval for the slope. So this is the R code that you use to get a confidence interval from your regression output. Confint of your fitted model, and which I always call fit. All right, so notice that it gives you a confidence interval for the intercept, which we can ignore. We're not going to use any of the output for the intercept. It usually has no meaning. All statistical software packages still give you information on it. All right, the bench press is the one that we're interested in. Now, what are these column headings? Well, that actually tells you your confidence level. Basically, it's telling you that the t-critical points it used to calculate this confidence interval are the ones that separated the middle 95% from the lower 2.5% and the upper 2.5%. And if you said that in terms of a percentile, this critical point would be the 2.5 percentile, right? Because it has 2.5% below it. But how much does this one have below it? It has 97.5 below it. And so that's where those numbers come from. If you subtract them, you can always get your confidence level. So that's how you know what confidence level it gave you. The default is 95%. And you can change the default in that function if you need another confidence level. All right, so we've got our confidence interval. Now let's go ahead and interpret it. So I'm going to go ahead and write this with the parameter in between. And I'm going to round this to 3 decimal places. So 0.973 less than beta 1 less than 1.432. And we need to remember that our beta 1 is our change in y's, which is our change in deadlift, with a change in x, a change in bench press. Okay? All right, so here we go. And we're going to think about it in terms of the deadlift increasing by the amount of these endpoints with a 1 pound increase in bench press. Remember, it's always a 1 unit increase in your x. We could do a 100-pound increase, but then we just have to multiply the endpoints by 100. Okay, so, but we're going to do it just in terms of 1 this time. So we are 95% confident that for each additional pound pressed in bench press, mean deadlift increases by 0.973 to 1.432 pounds. Okay, so do you see the ingredients there? For each 1 unit increase in my x, which is bench press, and 1 unit is 1 pound. Don't forget your parameter, mean. Mean y increases or decreases by those endpoints. Here we've got positive numbers, so it's increasing. All right, so that's a confidence interval for the slope. And now we can get confidence intervals for our predicted values. So we have 2 options. For a given x value, we can give a confidence interval for the predicted average value of y. And we can also give a prediction interval for the next y. Now in business, people want to know what's going to happen when they do one ad campaign, right? They want to know the prediction interval for the next time they do something. But often, those intervals are too wide because when you make an interval about one value, your standard error is going to be much larger. You're going to have more variability because you're just looking at one value instead of the average of several values. All right, so lots of times we just report both when people ask for a prediction interval. Now these are the kind of ugly looking formulas for the prediction intervals, for the mean response and for the individual y. We're going to let R calculate them for us. I want you to know how to interpret these and some of the qualities of these intervals. So what I've done here is I've started with a simple graphic that I made in R. And what this is the fitted line to our data set, which is right here in the middle. Okay? And then I've got this inner set of confidence bands that's the 2 dotted lines that are closest to my predicted value line. And then I've got my outer 2, which are dotted lines in red. Those are the farthest away from my center line. The 2 inner bands are the confidence limits for the mean response, for the mean Y. And the outer ones and the outer bands are for the individual Y. So what I want you to know about these is that your prediction intervals for one are going to be wider than your prediction intervals for the average response. All right, another thing that I want you to notice is, it's kind of hard to see on the outer red lines, but you can see it on the inner blue lines. Notice that they curve like this. The further away you are from the mean X value, the wider the interval is going to get. So the individual Y interval is always going to be wider, but then the further away that you get from the mean X value, from the mean bench press, so the further out this direction, your intervals are going to get wider in general anyway. All right, so let's take a look at what we're looking at here. So let's say that we wanted to make a prediction based on a bench press of 225 pounds. Well, where's my single value prediction? It's right here. So it's a little bit less than 350. And I could plug that into my regression equation to get the exact number, right? I could take my regression equation, plug 225 into it, and get an estimate of the deadlift. But now we're saying that's not good enough. I don't want just a one number estimate. I have a standard error, I've got a measure of variability, I've got an estimate of my thing I'm trying to estimate. Let's buffer how far off I think my guess is with a confidence interval. So we've got our confidence interval for the average deadlift at a bench press of 225 right here. And that goes from somewhere roughly like around, I don't know what, 325, 320, 310, up to a little over 350. And then I've got my confidence interval for the next deadlift at a bench press of 225. And that's somewhere around 275 up to somewhere around 400. Okay? And so what I've done is I computed confidence intervals for every single value of X and just graphed them here for you. All right, so now let's take a look at those specific intervals for a bench press of 225. So in R, you're going to use the predict function. Okay? You're going to use your fitted model, which I always call fit, and then you're going to give it what it calls new data. You're going to name an individual X value, whichever one you want to make the prediction from. I chose 225, and you're going to make it into a data frame. Just use data.frame around it. And then comma, what type of interval you want. The one that says confidence is for the mean Y. And the one that says prediction is for the individual Y. Okay? Now, notice that my fitted value is the same for both of these. That's because that is plugging 225 into the regression equation and figuring out what Y value that corresponds to. And it ends up being 344.1657 pounds. But notice that the confidence interval, the lower and upper limit, for these two different types of intervals are different. Notice that the one that's for the mean Y is narrower. It goes from 320 to 368. And notice that the one for the individual Y is much wider. It goes all the way from 281 to 407. All right, so let's take a stab at interpreting these. So let's interpret the interval for the mean response at a bench press of 225 pounds. So that's these numbers right here. Well, remember, you always start with your confidence level, so we're 95% confident that for bench presses of 225 pounds, the average deadlift is between 320.65 and 367.68 pounds. Hopefully that interpretation makes sense. You probably should be getting pretty good at interpreting confidence intervals at this point. Now let's take a stab at interpreting the interval for the next Y. So interpret the interval for the next deadlift at a bench press of 225 pounds. Start it out the same way all of your other confidence intervals go. We are 95% confident that for any randomly selected bench press of 225 pounds, the deadlift will be between 281.07 and 407.26 pounds. So notice how this is talking about a single Y. The previous one was talking about the average Y. Okay, so that's how you interpret your prediction intervals. Now let's talk about what we do if we have a violation of the regression assumptions. What do you do if there's a violation of the assumptions? Well, notice that I ignored the gas tax regression assumption checks. Let's look at them now. So you can see that on the residuals versus predicted plot, this does not look like there's a constant error variance, right? It looks a little bit like what we call a fan shape. They get wider as you go. And there's a struggle here in my QQ plot too. It's not looking super linear. All right, so we've got the variance appears to be increasing with the fitted values, and then there's California out here hanging out doing its own thing, and also the QQ plot is not very linear. So take a look at what happens if I take the logarithm of both my x and my y and I plot the data. That looks linear, and it looks like it might solve some of our problems. Now make note, I know we've talked about this before, that in R and in many statistics software and books, they're going to use that to denote the natural log. If you have just log in R, that's going to be the natural log. That's the log base E. The log base 10, you have to put a 10 after it. So I know that might be a little unusual for those of you who are used to pure math, but that's just the way it is in statistics. All right, and so when I take the natural log and run the regression, look what happens. My residuals plot looks much better. It looks much more like the errors are going to have mean 0, and like we took care of that variability problem a little bit more. And the QQ plot looks a little bit better too. It's not perfect. I probably could tweak this with some different transformations, but my point is that you can do a transformation when you have a violation of the assumptions. Some common transformations are taking the logarithm, the square root of the data, 1 over the data, 1 over the square root of the data, etc. All right, and our last topic in simple linear regression is outliers, leverage, and influence. We're going to visit these much more in depth than multiple regression, but we're going to introduce them now so you get an idea of what they are. So points with y values that are far from the regression model are called outliers. Outliers can be points with large residuals. Notice how this point is way above the line, so that's going to have a large residual. Points with x values that are far from the mean of the x's, so far in this direction or this direction, are called leverage points. So notice this red x is really far from the rest of the x's, so that we're going to say that has high leverage. And then when you have a point that is has high leverage and is combined maybe with a high residual, it's said to be influential if leaving it out yields a substantially different regression model. If a point is influential, you should check to make sure there is not an error. Not all influential points have a high residual. Always look at the scatter plot. Find out why it's influential, and if in doubt, run both models. So let's practice a couple of these. Tell me whether this point is a high leverage point, if it has a large residual, and if it's influential. So first of all, is it far away from the mean of the x's? No, not in particular. So I'm not going to say it has high leverage. What about a large residual? Yeah, the line is probably going to fit right through this data. This point is far away in the y direction, so I'm going to say it has a large residual. Is it influential? If I took this out, would it change my regression model? Probably not. So we're going to say not high leverage, it does have a large residual, and it's not very influential. All right, how about this one? So first of all, does it have high leverage? Is it far away from the rest of the points in the x direction? Yes, it is. So I'm going to say this one has high leverage. Does it have a large residual? The line is probably going to be right here. It's not particularly far away in the y direction, up or down. It's pretty close, so I'm going to say it does not have a large residual. And if I removed it, I think that my model would be the same, so it's not going to be influential. So this one has high leverage, a small residual, and it's not very influential. All right, and we've got one more. Does this one have high leverage? Yes, it is far away from the others in the x direction, right? Let's not talk about it having a large residual or not, because it's debatable where the line would be, right? If I took this point out, I think my line would probably go here, right? But if this point was in here, when we're trying to minimize that sum of squared residuals, if I put my line here, this would make a gigantic squared residual. And so a computer package is going to try to find the line that minimizes those, and it's probably going to follow that point, because putting all these little squares in here isn't as bad as putting that one big gigantic square in. So we're going to say that this point is influential. If I removed it, it would likely change my regression model. So high leverage and very influential. We won't always be able to picture leverage and influence, especially in multiple regression, so we're going to need some numerical methods, but we're going to cover those when we get to multiple regression.